Welcome to Sleepy Time Stories. Hey, dear friends, let your mind drift back to a moment on the edge of a world that's about to fade away. Not slowly, not across endless ages, but in what geologists call a heartbeat. It's 12,800 years ago, and Earth is finally shaking off the deep chill of a frozen epoch. Massive rivers of ice that once pushed from the top of the planet almost down to where a city called New York will someday rise are now melting back. The planet is taking a deep breath, loosening its muscles, returning to life. Then something happens. Something so shocking that it will echo through scientific arguments for the next 13 millennia. The woolly mammoths wandering across the grasslands of a future North America have no idea they're living through their final chapter. The enormous ground sloths, some rearing up 20 feet tall on their hind legs, don't know their days are numbered. Saber-toothed cats, giant beavers the size of black bears, camels, horses, dire wolves. None of them realize that within just a few hundred winters, they'll all be gone, erased, only bones and faint memories pressed into the earth. And here's what makes this mystery so captivating, so endlessly argued over. Nobody agrees on what killed them. Was it a comet? Did something from deep space crash into our atmosphere, breaking into thousands of pieces, setting fire to an entire continent and throwing the planet back into an ice age just when things were improving? That's what some scientists believe, and they point to strange materials in the dirt, microscopic diamonds that only form under extreme pressure, spikes in platinum, tiny magnetic beads, all signs of a cosmic collision. Or was it something completely different? A massive flood of melted glacial water pouring into North Atlantic, shutting down the ocean currents that keep Europe mild, triggering a climate catastrophe that spread around the globe. That's another idea, and it has its own strong evidence. Or maybe, and this is where it gets truly unsettling, maybe it was us. Maybe humans spreading into the Americas for the first time, armed with sharp stone tools and working in organized hunting groups, simply killed every big animal worth chasing. Overkill, a slaughter so complete that 3/4 of North America's large mammal species disappeared forever. The honest truth is, we still don't know for sure. And that's exactly why this story is perfect for falling asleep to. Because I'm not here to give you easy answers. I'm here to walk you slowly through one of the most fascinating and controversial mysteries in all of ancient climate science. If you're settling in for the night, wherever you are, just know that you're sharing this journey with people all over the world. What we do know is this. Around 12,800 years ago, Earth entered a period that scientists call the Younger Dryas. It's named after a small Arctic flower called Dryas octopetala that suddenly appears in fossil layers across Europe. This was a climate event that should never have happened. The planet was warming. Ice was melting. Then suddenly, violently, temperatures plunged. In some places, it got as cold as it had been at the peak of the Ice Age. And this cold snap lasted not for a few years, not for a few decades, but for 1,200 years. 1,200 years of unexpected, devastating cold. To put that into perspective, that's longer than the time between Charlemagne's empire and today. Imagine if our climate suddenly shifted back to Ice Age conditions right now and stayed that way until the year 3200. That's what the Younger Dryas did to our ancestors. Glaciers that had been retreating started advancing again. Sea levels that had been rising stopped and then dropped. Ecosystems that had been adjusting to warmth suddenly had to cope with cold again. And something, maybe the cold, maybe something else, maybe a combination of factors we're still trying to understand, drove dozens of species into extinction. This is the story of that vanishing world. The evidence for what happened, the theories about why it happened, and the ongoing scientific battle to understand one of the most dramatic climate events in recent geological history. We'll look at cosmic impacts in ocean currents, at ancient hunters and giant beasts, at microscopic diamonds and continent-spanning fires. Because 12,800 years ago, something ended. An entire era of Earth's history came to a close. And in the ashes of that ending, our modern world began to take shape. The question is, what actually happened? Let's go back to a world you wouldn't recognize. 15,000 years ago, Earth was a fundamentally different place. Not just colder, not just different, but transformed in ways that would seem alien to modern eyes. This was the late Pleistocene, the tail end of the last great ice age. And if you could stand on what's now the coast of New York City, you wouldn't see ocean. You'd see land stretching another 100 miles out to sea, forests and grasslands where today's ships sail through deep water. The ice sheets were still there, still massive, but they were beginning their long retreat. In North America, the Laurentide ice sheet covered everything from the Arctic down to what's now New York, Chicago, and Seattle. We're not talking about ordinary snow. We're talking about ice 2 miles thick in places. So heavy it was pressing the Earth's crust down like a finger pushing into soft clay. The weight was so enormous that the land is still rebounding today, thousands of years after the ice melted. Parts of Canada rise several millimeters per year, slowly recovering from that ancient compression. But here's what made this world spectacular. All the water locked up in ice had lowered global sea levels by nearly 400 feet. Coastlines extended far beyond their modern positions. What we call the English Channel was a river valley. You could walk from France to Britain without getting your feet wet. Indonesia was connected to mainland Asia by a vast land called Sunda, larger than modern India. Australia, New Guinea, and Tasmania formed a single massive landmass called Sahul. And then there was Beringia. The land bridge connecting Siberia to Alaska wasn't just a narrow strip of frozen tundra. It was a subcontinent unto itself, 1,000 miles wide in places, a vast grassland ecosystem that supported herd beyond imagination. This was the highway that brought humanity to the Americas. But it wasn't empty. It was teeming with life. The megafauna, that's what we call them now. But the name doesn't do them justice. These weren't just big animals. They were monsters, creatures that would make modern elephants look modest. In North America, Columbian mammoths stood 14 feet tall at the shoulder and weighed up to 10 tons. Their tusks could reach 16 feet long. Massive curved weapons and tools that they used to strip bark from trees and dig through snow to reach vegetation beneath. But the mammoths weren't even the biggest things out there. American mastodons roamed the forests, browsing on leaves and branches with their strange cone-shaped teeth. Giant ground sloths, some weighing up to 4 tons, stood on their hind legs to reach high branches. Their huge claws could tear through wood and defend against predators. Some of these sloths were so large they likely had few natural enemies once they reached adulthood. Then there were the predators. Short-faced bears that stood 12 feet tall on their hind legs, possibly the largest meat-eating land mammal that ever lived. They had long legs built for speed, able to run down prey across open grasslands. Saber-toothed cats prowled the landscape, their enormous canine teeth not just for show, but precision tools designed to deliver deadly bites to the throats of massive prey. Dire wolves hunted in packs, larger and more muscular than modern wolves, with bone-crushing jaws that could snap the leg bones of bison and horses. American lions, a quarter larger than modern African lions, range across the continent. Giant beavers the size of black bears built dams in rivers and lakes. Armored glyptodonts looking like Volkswagen-sized armadillos grazed peacefully with shells too tough for most predators to break through. The skies weren't empty either. Territorian birds, similar to condors but with 12-foot wingspans, soared overhead, watching for carrion or perhaps small prey they could snatch and carry away. This wasn't some struggling ecosystem at the edge of extinction. This was abundance. The grasslands and parklands at the edge of the ice sheets were incredibly productive, fed by mineral-rich meltwater and supporting plant growth that could feed huge populations of plant eaters. The cold climate actually helped. Less evaporation meant more available water. Seasonal freezing preserved organic matter instead of letting it rot, creating rich soils that exploded with growth during short but intense summers. Europe had its own megafauna collection. Woolly mammoths, smaller than their American cousins but perfectly adapted to extreme cold with their thick coats and small ears. Cave bears that weighed up to a ton and competed with humans for shelter in limestone caverns. Woolly rhinoceroses with 2 horns and dense fur, built like living tanks. Giant elk with antlers spanning 12 feet, the largest antlers ever evolved, so massive that males probably shed them every year just to survive winter when food was scarce. And everywhere there were humans. Not many, not yet, but they were there. And they were getting better at being human, with each passing generation. In North America, they were called the Clovis people, named after distinctive spear points first found near Clovis, New Mexico. But they weren't just one tribe or one group. The name represents a technological tradition, a way of making tools that spread across the continent with remarkable speed. Clovis points are works of art, carefully crafted from high-quality stone using techniques that modern flint-knappers struggle to copy. These weren't crude stone chips. They were precision instruments, symmetrical, aerodynamic, with fluted grooves running up both sides that allowed them to be attached securely to spear shafts. The Clovis people were sophisticated hunters. They understood animal behavior, migration patterns, seasonal movements. They knew how to work together, how to organize group hunts that could bring down animals 10 times their size. Archaeological sites show mammoth kills where multiple animals were taken at once, butchered systematically with every useful part carried away or processed on site. These weren't desperate scavengers. These were confident, capable people at the top of their game. They had fire and they knew how to use it, not just for warmth and cooking, but as a tool for managing the landscape, for driving game, for creating the kind of open grasslands that supported the megafauna herds. They made warm clothing from animal hides, sewn with bone needles using sinew thread. They created tools from bone, antler, and ivory when stone wouldn't do the job. They transported high-quality stone across hundreds of miles, indicating trade networks or seasonal movements over vast territories. And the world was warming. This is crucial. Around 15,000 years ago, Earth's climate began one of its periodic shifts from glacial to interglacial conditions. The massive ice sheets that had covered the northern continents were melting, not quickly by human standards, but inexorably, year by year, century by century. Summers were getting slightly longer, winters slightly milder. Grasslands were expanding as the climate became less harsh. The megafauna were thriving in this transition period, moving north as new territories opened up following the retreating ice. Everything was connected. The mammoths browsed on grasslands and spread seeds in their dung, helping plants colonize newly ice-free ground. Their feeding created open meadows that supported bison, horses, and camels. The predators followed the herds, keeping population balances, preventing any single species from dominating. Humans hunted carefully, taking what they needed but not destroying the resource base they depended on. Scavengers cleaned up the remains, recycling nutrients back into the ecosystem. It was a web of relationships refined over tens of thousands of years, and it should have continued. Based on Earth's orbital patterns in previous warm periods, the warming should have proceeded smoothly for thousands of years. The ice should have gradually retreated. Sea levels should have slowly risen. Ecosystems should have shifted northward at a pace that allowed species to adapt. Humans should have continued their expansion, their populations growing slowly as their territories expanded with the warming climate. That's what should have happened. That's what the pattern of earlier ice ages suggested would happen. But right at the moment when everything seemed ready for a smooth shift into a warmer world, something went terribly wrong. The warming stopped. Then it reversed. And when it was over, 2/3 of the megafauna species in North America would be gone forever. Picture yourself standing on a grassy plain in what will one day be called France. It's 13,000 years ago, and the world has been warming for thousands of years. The massive ice sheets that once covered half of Europe are finally pulling back. Your ancestors have watched this happen for generations. Every year, the glaciers retreat a little farther north. Every spring, new land appears where ice had stood for ages. The herds of horses, bison, and reindeer are thriving. Rivers run full of meltwater. Forests are starting to creep back into territories that haven't seen trees in 50,000 years. Life is becoming easier. Your people are expanding, developing new tools, creating art that will still be admired 15,000 years in the future. The Ice Age is ending. Everyone can feel it. The long winter humanity is finally coming to a close. And then, almost overnight in geological terms, everything shifts. The warming stops. Not slowly, not across centuries, but abruptly. Within a single human lifetime, maybe within one generation, the world plunges back into winter. Temperatures fall. In some parts of the northern hemisphere, the thermometer drops by as much as 10 degrees Celsius. That might not sound like much until you realize that's the difference between the climate of England and the climate of northern Scandinavia. The difference between forest and frozen tundra. the difference between plenty and survival. The glaciers that had been retreating for thousands of years stopped their withdrawal. In some places, they began growing again. Lakes that had been ice-free for centuries freeze solid. Plants that had spread onto newly exposed ground die off, replaced by tough tundra species that can endure the renewed cold. The animals follow. Species that have been thriving in the warming world find themselves struggling again, pushed back into smaller refuges, competing for shrinking resources. This wasn't supposed to happen. Earth's climate had been on a steady warming trend for over 5,000 years. All the evidence suggested the ice age was ending. But something had broken Earth's thermostat, and now the planet was falling back toward full glacial conditions. Scientists call this period the Younger Dryas. The name comes from a small Arctic flower, Dryas octopetala, with 8 delicate white petals and leaves that hug close to the ground. It's a plant that thrives in the coldest conditions, growing on windswept tundra where almost nothing else can survive. When geologists studying ancient sediment cores and pollen records found huge spikes in Dryas pollen around 12,800 years ago, they knew something dramatic had happened. This flower, which had been rare in European sediments during the warming period, suddenly dominated the landscape again. The cold had returned. The Younger Dryas lasted roughly 1,200 years, from about 12,800 to 11,600 years ago. But those numbers, precise as they sound, don't capture the violence of the transition. The archaeological and geological evidence suggests the cooling didn't ease and gradually over centuries. It happened fast, catastrophically fast. Ice cores from Greenland tell the story most clearly. Scientists drilling into ancient ice can read climate history year by year, sometimes season by season, in the layers of frozen snow that have built up over many thousands of years. The chemical makeup of each layer, the types of dust and pollen trapped in the ice, the ratios of different oxygen isotopes in the water molecules themselves. All these details create a climate record more precise than any written history. And what those ice cores show is startling. The shift into the Younger Dryas happened over decades at most, possibly even faster. Some researchers think temperatures in Greenland might have dropped by several degrees within a single decade. That's not climate change as we usually think of it. That's climate collapse. The geological evidence for this rapid transition shows up everywhere, not just in ice cores. Lake sediments from across Europe and North America show dramatic shifts in the types of microscopic organisms living in the water. Species that prefer warmer conditions vanish suddenly from the record, replaced by cold water specialists. Tree rings from ancient stumps preserved in peat bogs show years of stunted growth starting exactly at the Younger Dryas boundary. Some trees that have been growing for centuries simply stopped growing altogether, entering a kind of suspended animation as they waited for better conditions that wouldn't arrive for over 1,000 years. Pollen records paint an even more detailed picture. As temperatures dropped, forests retreated rapidly southward. Oak and elm pollen, which had been increasing in northern sediments during the warming period, virtually disappears at the Younger Dryas boundary, replaced by pine, then by tundra grasses and sedges, and finally by that telltale Dryas flower. It's like watching a time-lapse video of the ecosystem rewinding, undoing thousands of years of warming in just decades. The temperature drop wasn't uniform across the planet. The northern hemisphere, especially regions around the North Atlantic, got hit hardest. Temperature reconstruction suggests drops of 8 to 10 degrees Celsius in Greenland and northern Europe. Britain, which had been warming nicely, plunged back into near-glacial conditions. Parts of North America saw similar dramatic cooling. But here's where it gets interesting. The southern hemisphere didn't cool nearly as much. Some regions actually warmed slightly during the Younger Dryas. This imbalance is crucial because it tells us something important about the mechanism behind the cooling. Whatever caused the Younger Dryas, it wasn't a global phenomenon like a drop in solar radiation or a huge volcanic eruption putting dust into the upper atmosphere. Those would have affected both hemispheres roughly equally. No, this was something that specifically disrupted the climate of the northern hemisphere. The puzzle deepened when scientists realized just how abrupt the end of the Younger Dryas was. The ice cores show that the warming that finally ended this cold snap was even more dramatic than the cooling that began it. In some locations, Temperatures might have risen by 10 degrees Celsius or more within just a few years, perhaps within months in some regions. Think about that for a moment. The entire 1,200-year cold period was bookended by two catastrophic climate transitions. First, a plunge into cold that happened within decades. Then, over a millennium later, a surge back to warmth that happened even faster. Earth's climate was behaving less like a gradually adjusting thermostat and more like a light switch being flicked on and off. These aren't the time scales climatologists expect for natural climate variation. Ice ages are supposed to come and go over tens of thousands of years, driven by slow changes in Earth's orbit and the wobble of its rotational axis. Even shorter climate fluctuations typically take centuries to develop, but the Younger Dryas developed in decades and ended in years. Something had triggered a rapid, catastrophic change in the way Earth's climate system operates. Some kind of threshold had been crossed, flipping the system from one state to another almost instantaneously on geological timescales. Scientists first identified the Younger Dryas in the 1930s, but for decades it remained a geological oddity, a strange blip in the climate record that nobody could quite explain. The real breakthrough came in the 1980s when oceanographers studying ocean currents began to understand how quickly the circulation patterns in the North Atlantic could change. They discovered that relatively small changes in ocean salinity or temperature could potentially shut down major current systems. And when those currents shut down, they could drag entire hemispheres into renewed ice age conditions. But that just pushed the mystery back one level. What could cause such a dramatic change? What could dump enough fresh water into the North Atlantic to disrupt ocean circulation on such a massive scale? The ice sheets were melting, sure, but they'd been melting gradually for thousands of years. Why would the meltwater suddenly cause problems at exactly 12,800 years ago? Then, in 2007, a team led by nuclear physicist Richard Firestone proposed something nobody was expecting. What if it wasn't just climate change? What if something had hit us? Not a metaphor, not a gradual environmental shift, but something from space. Something that struck North America with enough force to change the entire planet's climate in a matter of years, maybe even months. The Younger Dryas impact hypothesis wasn't suggesting a gentle cosmic visitor. It proposed that around 12,800 years ago, Earth encountered the debris field of a fragmenting comet. Multiple chunks of ice and rock, some possibly several kilometers across, either slammed into the ice sheets covering North America or exploded in the atmosphere above them. The result would have been catastrophic. Immediate devastation across the impact zones. Massive wildfires spreading across the continent. Enough debris thrown into the atmosphere to darken skies for months or years. And most significantly, enough energy dumped into North American ice sheets to trigger rapid melting, flooding the oceans with cold fresh water and disrupting the currents that kept the northern hemisphere warm. The first piece of evidence was subtle but intriguing. Nanodiamonds. These are microscopic diamond crystals that form only under conditions of extreme pressure and temperature, the kind you get during meteor impacts or nuclear explosions. Firestone's team reported finding concentrations of nanodiamonds in sediment layers dating to exactly 12,800 years ago. Not just at one site, but at multiple locations across North America and Europe. These weren't random diamonds weathered out of ancient geological formations. They appeared suddenly in the sediment record, right at the boundary between the Clovis period and the Younger Dryas, right where you'd expect to find evidence of a cosmic impact. Then there were the magnetic spherules. These are tiny balls of iron and other metals that form when rock is vaporized by intense heat and then condenses in the atmosphere. You find them at known impact sites like the Chicxulub crater in Mexico, where the dinosaur-killing asteroid struck 66 million years ago. Firestone's team found similar spherules in the same 12,800-year-old sediment layer. Their microscopic structure suggested they had been subjected to temperatures exceeding 2,000 degrees Celsius. That's hot enough to melt rock, hot enough to vaporize it. But the most compelling evidence, at least at first, was platinum. Platinum is rare on Earth's surface. Most of it is locked deep in the planet's core, or it arrived here on meteorites after Earth's crust had solidified. When you find sudden spikes in platinum concentration in sediment layers, it usually means something from space delivered it. The team reported finding platinum anomalies at the Younger Dryas boundary layer across dozens of sites. Not huge amounts, but statistically significant increases that appeared suddenly and then declined just as quickly. The pattern looked exactly like what you'd expect from an extraterrestrial impact. And there was more. At sites across North America, archaeologists had long noted something called the black mat, a layer of dark sediment rich in carbon and organic material that appeared right at the boundary between the Clovis period and what came after. The impact hypothesis offered a different explanation. What if the black mat represented the remains of massive continent-wide wildfires triggered by the impact event? If a fragment of a comet had exploded in the atmosphere over North America, the airburst would have released thermal radiation intense enough to ignite forests across thousands of square miles. The resulting firestorm would have burned across the continent for weeks or months, consuming everything flammable. The ash and charcoal from these fires would have settled into a distinct layer, creating exactly the kind of black mat observed in the archaeological record. The scenario they proposed was apocalyptic. Picture this. It's a normal day 12,800 years ago. Clovis hunters are tracking mammoth herds across the Great Plains. Families are gathering around fires in temporary camps. Children are learning to shape stone tools from their elders. Then, without warning, the sky lights up. Multiple fireballs, each one brighter than 1,000 suns, streak across the heavens. Some impact directly on the massive ice sheets covering Canada. Others explode in the atmosphere, releasing energy equivalent to thousands of nuclear weapons. The thermal pulse ignites everything it touches. Forests burst into flame from horizon to horizon. Animals caught in the open are incinerated instantly. Those in sheltered valleys might survive the initial blast only to suffocate in the smoke and heat that follows. The ice sheets absorb devastating amount of energy. Within hours, meltwater is cascading off the glaciers in unprecedented volumes. Within days, massive floods are roaring south, carving new channels and drowning river valleys. Within weeks, enough cold fresh water is pouring into the North Atlantic to disrupt ocean currents, shutting down the heat conveyor belt that keeps Europe and eastern North America warm. And the humans, the Clovis people who've been thriving just moments before, those near the impact zones are simply gone, vaporized or buried under millions of tons of debris. Those farther away face a rapidly collapsing world. The megafauna they depended on are dying from the fires, the climate shift, and the sudden loss of food plants. Their sophisticated hunting culture, so perfectly adapted to late Ice Age conditions, becomes useless in a matter of years. But as compelling as this evidence seemed, it was far from universally accepted. For every researcher who looked at the nanodiamonds and platinum spikes and saw proof of an impact, there was another who saw something else entirely. The scientific response wasn't subtle. Within months of Firestone's team publishing their findings, laboratories around the world started trying to replicate their results. And that's when things started falling apart. First came the nanodiamonds. Multiple independent teams went to the exact same sites where Firestone's group had found them. They collected samples using identical methods. They analyzed them with the same equipment, and they found nothing. No nanodiamonds, no impact spherules, no evidence whatsoever of cosmic catastrophe. Eventually, over a dozen independent studies had searched for the impact signature and come up empty. That's not a sampling problem. That's a reproducibility crisis. But it gets worse. Some labs did find nanodiamonds in the Younger Dryas boundary layer. They also found them in layers above and below the boundary, and in layers from completely different time periods. Turns out nanodiamonds aren't that rare. They form in forest fires. They show up in volcanic eruptions. They can even form in the soil through normal geological processes. Finding nanodiamonds in a sediment layer doesn't mean a comet hit. It just means something burned or got compressed. The platinum spike ran into similar problems. Initial studies showed dramatic increases in platinum concentrations right at the Younger Dryas boundary. But when other researchers looked at the same sites with better analytical techniques, the spike disappeared. What looked like an anomaly was actually just normal background variation amplified by small sample sizes and selective reporting. The charcoal evidence posed its own problems. Yes, there's widespread evidence of burning across North America at the start of the Younger Dryas, But there's also evidence of burning in dozens of other periods throughout the last 100,000 years. Climate changes cause fires. Droughts cause fires. Lightning causes fires. Humans cause fires. Finding evidence of widespread burning doesn't tell you what caused the burning. Several research teams pointed out something crucial. The peak in charcoal deposits doesn't actually align precisely with the Younger Dryas boundary. In many locations, the increase in burning starts hundreds of years before the cooling begins. In others, it continues for thousands of years after. If a comet impact caused the fires, you'd expect synchronicity, everything burning at once precisely at the moment of impact. Instead, you see a complex pattern of fires spread across centuries, which look a lot more like climate-driven environmental change than cosmic catastrophe. Then there's the crater problem, or rather the lack of a crater problem. If something big enough to cause a global catastrophe hit Earth 12,800 years ago, it should have left a mark, and we're pretty good at finding impact craters. We've identified hundreds of them, from tiny depressions barely visible on the landscape to massive scars like Chicxulub. So where's the Younger Dryas crater? The impact proponents have offered various explanations. Maybe it hit the ice sheet and the evidence melted away. Maybe it exploded in the atmosphere. Maybe it broke into dozens of smaller pieces. But each explanation creates new problems. An ice sheet impact large enough to trigger global cooling should still leave geological evidence. An atmospheric explosion wouldn't produce nanodiamonds or spherules. Multiple impacts should show up as multiple distinct layers, not a single boundary. Some researchers propose that a crater-like structure under Greenland's ice sheet might be the smoking gun. But when geologists dated the ice above it, they found it was either much older than the Younger Dryas or possibly even younger. Either way, it doesn't align with the timing they needed. The timeline itself became a major source of controversy. When you look closely at the dating, it starts to blur. The platinum spike in some locations dates to 12,950 years ago. In others, 12,700 years ago. The nanodiamond layer varies by similar margins. The charcoal peaks are spread across several centuries. If a comet hit Earth, all the evidence should date to exactly the same moment. The fact that it's smeared across centuries suggests something else is going on, something that happened gradually, not catastrophically. Geologists propose alternative explanations for basically every piece of evidence. The magnetic spherules could have formed from industrial contamination or even modern pollution working their way down into older sediments. The supposed cosmic materials might actually be volcanic. The Younger Dryas began during a period of increased volcanic activity, and volcanic eruptions can produce many of the same signatures as impacts. The meltwater flooding could be explained much more simply by the natural dynamics of ice sheet collapse. No impact required, just regular ice age physics. Ice dams form, ice dams break. Floods happen. It had happened before the Younger Dryas. It happened during it. It happened after. By the mid-2010s, the scientific community's position had solidified. Most researchers remained deeply skeptical of the impact hypothesis. Major review papers concluded the proposed impact signatures weren't reproducible, weren't unique to impacts, or weren't actually synchronous with the Younger Dryas boundary. But here's what makes this story fascinating. The impact proponents didn't give up. They kept looking, kept refining their evidence, kept publishing new findings. The debate became increasingly technical. Arguments about statistical methods, laboratory protocols, sampling strategies, the kind of details that are absolutely crucial to determining what actually happened. Because that's how science resolves controversial questions. Not through dramatic breakthroughs, but through painstaking accumulation of evidence, replications, reanalyses, and eventually consensus. What's interesting is that both sides agree on the fundamental observations. Yes, the megafauna went extinct. Yes, the Clovis culture disappeared. Yes, the climate changed dramatically. Yes, there's evidence of widespread fires. The disagreement isn't about whether these things happened. It's about why they happened and whether a single catastrophic event can explain them all. The critics argue that invoking a comet impact is unnecessary. The climate change alone, driven by changes in ocean circulation, can explain the extinctions and cultural disruptions. The fires can be explained by climate-driven droughts. The unusual minerals can be explained by volcanism or contamination. You don't need a cosmic catastrophe when terrestrial processes work just fine. And that's where the debate stands today. Unresolved. Both sides publishing papers. Both sides claiming the evidence supports their interpretation. Both sides pointing out flaws in the other's methodology. This isn't a failure of science. It's science working exactly as designed, testing ideas, demanding evidence, refusing to accept conclusions until they're proven beyond reasonable doubt. The controversy has actually been productive. It's driven researchers to develop better dating methods, more sensitive analytical techniques, more rigorous sampling protocols. It's forced everyone to think more carefully about what evidence would definitively prove or disprove an impact. It's led to discoveries about Younger Dryas climate dynamics that wouldn't have been made otherwise. But for the question that started all this, whether a comet caused a Younger Dryas catastrophe, the answer from the scientific mainstream remains decidedly skeptical. Possible, maybe. Proven, not even close. The meltwater pulse theory offers a different explanation. Picture North America at the end of the last ice age. Almost half of it is buried under the Laurentide ice sheet, a frozen shield stretching from the Arctic down into the northern United States. To the west, another wall of ice clings to the Rockies. Between and beneath these frozen giants, the melt has already begun. Summer sun chews at the ice margins. Glaciers creak and groan. Rivers pour out from blue tunnels at the ice front, loaded with silt and gravel. But not all that meltwater escapes to the sea. Some of it pools, trapped behind ridges of ice, rock, and frozen soil. Gigantic inland seas form. The greatest of these was Lake Agassiz. At its full extent, it covered an area larger than all the Great Lakes combined, larger than modern Germany or France, and it was held back by a dam made not of concrete but of ice. That's the heart of the meltwater pulse theory. You don't need a comet if you already have a loaded gun sitting in the middle of a warming world. As the climate warmed, these giant lakes grew. The ice dams were never stable, crevassed, fractured, constantly melting at the edges. But for thousands of years, they held. Then, according to this hypothesis, they didn't. Imagine what happens when a dam fails. A wall of water racing downhill at highway speeds, ripping up forests, boulders, soil, anything in its way. Now scale that up from a reservoir to an inland sea thousands of kilometers across. When people talk about Lake Agassiz draining, the word is far too calm. We're talking about catastrophic flood events, or more likely a series of them, as the lake found new outlets to the ocean. For the Younger Dryas, the critical part is where that fresh water went. Most versions focus on a catastrophic outburst into the North Atlantic. The idea is simple but powerful. Take an entire continent's worth of fresh water, release it rapidly into the ocean, and you change how that ocean works. To see why, you have to understand the Atlantic Meridional Overturning Circulation, or AMOC. You can think of it as a conveyor belt that moves heat around the planet. Warm water flows north at the surface, gives up its heat to the atmosphere, helping keep places like Western Europe far milder than their latitude would suggest. Then, cooled and dense, it sinks into the deep ocean and flows back south. Now imagine what happens if you dump a huge volume of cold, fresh water right where that conveyor belt is supposed to sink. Fresh water is less dense than salty water, less eager to sink. Pour enough into the North Atlantic, and the surface layer becomes lighter, more buoyant. The engine that drives the overturning circulation stalls, or at least sputters badly. This is a key move. No impact, no comet, just physics. Ice sheets melt, lakes fill, dams fail. Fresh water floods into the Atlantic, AMOC weakens, and the climate snaps back to glacial conditions over large parts of the Northern Hemisphere. The Younger Dryas isn't an alien intrusion from space. It's a feedback loop in Earth's own climate system, a kind of cold whiplash triggered by the way oceans respond to sudden freshwater loads. There's evidence that something like this can happen. In Greenland's ice, trapped air bubbles and layered snowfall record past climates in exquisite detail. When scientists drill deep into that ice, they see rapid shifts in temperature linked to changes in ocean circulation, not just during the Younger Dryas, but at other times in the last glacial period. In marine sediments on the floor of the North Atlantic, Tiny fossils of plankton tell similar stories. Species are like warmer, salter waters suddenly replaced by species adapted to colder, fresher conditions. Layers of ice-rafted debris hint at changes in where and how sea ice formed. Geologists have mapped old shorelines of Lake Agassiz, strand lines, and abandoned spillways, deep channels carved by ancient floods. They found huge deposits of gravel and sand laid down by catastrophic flows. In some places, they can see abrupt drops in lake level, as if the water suddenly found a new escape route. In the North Atlantic, there are layers of freshwater-loving microfossils and changes in the chemistry of the sediments that suggest pulses of low-salinity water entering the ocean, dated to around the onset of the Younger Dryas. None of this is as dramatic as a comet explosion. There's no firestorm, no crater, no diamond-rich boundary layer you can point to. Instead, the evidence for meltwater pulses is more like a quiet chorus of clues scattered across the world, all humming the same tune. Even within the meltwater pulse framework, the details are messy. Exactly when did Lake Agassiz drain? Once? Many times? Did the water go east into the St. Lawrence in the North Atlantic, or north into the Arctic Ocean, or south through the Mississippi Basin into the Gulf of Mexico? Different studies suggest different routes at different times. Some reconstructions place the biggest outburst a bit before the Younger Dryas. Others put it right at the beginning. Some argue for multiple pulses. And then there's the AMOC itself. Did it fully shut down or just weaken? How sensitive is it to freshwater input? Modern climate models suggest it can be disrupted, but the exact thresholds are still debated. We're dealing with a chaotic system, not a simple on-off switch. Still, the broad picture remains compelling. A major freshwater event or series of events destabilizes the Atlantic circulation and plunges large parts of the northern hemisphere into a sudden, severe cold spell. Forests retreat. Ice sheets stop shrinking and start growing again. Species that have been moving north find themselves pushed back into refuges or wiped out entirely. Do we have to choose between these ideas? A lot of scientific debates get framed as either/or. Either a comet did it or meltwater did it. But the real world is rarely that clean. It's entirely possible that both stories hold part of the truth. Imagine a large impact, or a cluster of mid-sized ones, occurring over the Laurentide ice sheet. The explosion vaporizes ice, darkens the atmosphere with dust and soot, and ignites wildfires. At the same time, the shock waves and intense localized heating destabilize already fragile ice dams. Melt rates spike. Cracks propagate through the ice. A system already under stress tips over. In that scenario, the impact doesn't replace the meltwater pulses. It triggers or amplifies them. Or perhaps the primary cause was the internal dynamics of the climate system. The slow buildup of meltwater, the inevitable failure of ice dams, the weakening of the sea. In that version, if there was an impact, it was more of an unwelcome guest arriving at a party that was already going badly. Freshwater flooding could have made the climate system exquisitely sensitive. A relatively modest additional perturbation, dust, soot, or aerosols from an extraterrestrial event, might have pushed it that last crucial inch into a new, colder state. Or maybe there was no impact at all, and all of the strange evidence has other explanations. In that case, the meltwater pulse theories stand alone. For now, the jury is still out. What we can say is that the Earth at the end of the last ice age was not a stable place. It was a world in transition, an enormous, creaking system shifting from a glacial state to something more like the present. Ice sheets were collapsing. Sea levels were rising. Ecosystems were migrating. Humans and megafauna were moving into newly open lands. In such a world, it doesn't take much to cause big changes. A few extra degrees of warmth, a bit more meltwater in the wrong place, a slightly weaker current, or perhaps something bright and fast crossing the night sky. The meltwater pulse theory reminds us that you don't always need a single dramatic villain. Sometimes the most powerful forces in history are quiet ones. Water pooling behind ice, salt mixing with fresh, a current turning more slowly in the deep. And sometimes the real story isn't one cause or another, but the way multiple threads braid together. Ice, ocean, atmosphere, life, impact from above, pressures from below, all woven into one long, complicated event we now call the Younger Dryas. As we near the end of this journey, let your mind settle like sediment drifting down through ancient waters. The questions we've explored tonight don't demand answers before you sleep. The mystery of the Younger Dryas will still be there tomorrow, still debated in labs and conferences, still yielding new clues from ice cores and lake beds. But for now, you can let it all go. The mammoths and mastodons, the Clovis hunters and their fluted spear points, the comet that may or may not have fallen, the floods that may or may not have roared from melting ice. These are stories we tell ourselves to make sense of a world that is always changing, always surprising us. You are part of that long chain of storytellers and listeners, stretching back thousands of generations. And like all those who came before, you deserve rest. So close your eyes. Feel the weight of your blankets like the deep snow that once covered ancient lands. Let your breath slow to the pace of glaciers, to the rhythm of waves on a long-vanished shoreline. The world outside will keep turning. The stars will continue their slow march across the sky. And you, dear friend, can drift now into peaceful sleep. Carry with you only the softest echoes of this vanished world. Good night, sweet dreams.